Welcome linear algebra fans, a video on linear independence. As usual here, we'll start with a definition. We'll see a set of vectors that is linearly independent as well as a set of vectors that is not. We'll talk about how linear independence relates to non-singular matrices, and then we'll talk about how linear independence relates to describing the null space of a matrix as the span of a set of vectors. Okay, so to begin with the definition, here's the definition. Given a set of vectors, u1 to un, a true statement of the form alpha 1 plus u1 all the way out to alpha n, un equals 0 is called a relation of linear dependence. Okay, oftentimes we'll call this a zero linear combination. Now, one way we can always make a relation of linear dependence on the set S is to take 0 parts of each vector. That's kind of a silly way. We'll call that the trivial relation of linear dependence. Okay, so given a set S, our relation of linear dependence is a linear combination equal to 0. Every set S always has one relation of linear dependence. That is the trivial one, right? We could always take 0 parts of all those vectors and get out the 0 vector. So now the definition of linearly dependent. We say that the set of vectors u1 to un is linearly dependent if there's a non-trivial relation of linear dependence. Okay, if there's no such non-trivial relation of dependence, then we say that the set is linearly independent. Okay, so sort of to summarize this idea of a non-trivial relation of dependence, there has to be one constant alpha I that's not 0, at least one. Okay, if a set S has only the trivial relation of linear dependence, we say that S is linearly independent. So sort of a take-home message here, to address the question of linear dependence on any set, we'll always begin with a relation of linear dependence. So here's an example. Let's take the set S, u1, u2, u3 to u4 to be these 4 vectors. And let's explore the question of linear dependence on S. Okay, in order to explore the question of linear dependence on S, we'll start with a relation of linear dependence on S of the form alpha 1 u1 out to alpha 4 u4. Now, determining whether a certain vector, in this case the vector 0, can be written as a linear combination of some given vectors, in this case u1 to u4, we'll go ahead and have a look at the corresponding linear system. Now, of course, since the right-hand side is 0, that linear system is a homogeneous linear system. Okay, so the relation of linear dependence on S gives rise to a homogeneous linear system. Here is the coefficient matrix corresponding to that homogeneous linear system. Now, I haven't augmented by the 0 vector here because that won't change anything, but row reducing that homogeneous linear system, row reducing that matrix shows us that the homogeneous linear system does have a non-trivial solution. Okay, of course, the homogeneous linear system has 4 variables. We see that the row reduced echelon form shows 3 pivots, so we expect n minus r equal to 1 free variable. The homogeneous linear system has infinitely many solutions. Okay, in fact, here's the vector form of that solution: 2, minus 4, 3, 1 times x4. So, of course, one such solution we could find just by setting x4 equal to 1, which tells us one non-trivial relation of dependence on this set S. Okay, here's an example of that relation of linear dependence. Again, I'm just setting x4 equal to 1 from our vector form of the solution. So 2 u1 minus 4 u2 plus 3 u3 plus u4 is equal to 0, a non-trivial relation of dependence. So we see that S is linearly dependent. Now, of course, not every set is linearly dependent, so let's have a look at another example. Let's take the set S to be equal to v1, v2, v3, v4, and we'll show that this set, as it turns out, is linearly independent. Okay, so again, we'll consider a relation of linear dependence on this set S. Okay, here's that relation of linear dependence on the set S. I've used betas here, beta 1, v1 plus beta 2, v2 plus beta 3, v3 plus beta 4, v4 equal to 0. Of course, addressing the question of whether a vector is a linear combination of others requires us to consider a linear system. In this case, the linear system is again a homogeneous linear system. Here's the coefficient matrix for that homogeneous linear system. We can see that when we row reduce, we end up with R equals 4 pivots for n equals 4 variables. Of course, with R equals 4 pivots, there are n minus R equals to 0 free variables. Therefore, the homogeneous linear system has a unique solution. Of course, every homogeneous linear system has 0 as a solution, so 0 is that unique solution. Okay, since the only relation of linear dependence is trivial, we see that the set S is linearly independent. Now, as it turns out, linear independence is tied always to solutions of the corresponding homogeneous linear system. When we say always, there's a theorem. Here's the theorem. The theorem is that suppose S is a set of vectors and that A is the m by n matrix whose columns are those vectors. S is linearly independent if and only if the homogeneous system has a unique solution. Okay, so we'll go ahead and walk through the proof of this. We'll first prove the Q implies P statement by assuming that the homogeneous linear system has a unique solution. Okay, if the homogeneous linear system has a unique solution, well, that solution has to be the trivial solution. So the only way that a linear combination of the columns of the matrix A is 0 is if the coefficients of that linear combination are all 0. And this is exactly the definition of linear independence. Okay, so to prove the other direction of this if and only if proof, we're going to use the contrapositive. So instead of proving that P implies Q, the statement P implies Q, we'll instead prove that the statement not Q implies the statement not P. Okay, so in this case, the statement not Q that we'll assume is that the linear system A, 0 has a non-unique solution. If the corresponding homogeneous linear system does not have a unique solution, well, it must have infinitely many solutions because it's a consistent system. So we'll just go ahead and choose one of those solutions, a non-trivial one, and that solution gives us exactly a non-trivial relation of linear dependence on S. Okay, so the take-home message of this theorem is that to consider independence of the set S, we can have a look at a homogeneous linear system where the coefficient matrix has columns that are vectors in S. So here's an opportunity for you to explore this. on the worksheet, let's go ahead and have a look at whether this set of 3 vectors from C5 is linearly independent. Okay, so one way to examine this is to think about the corresponding homogeneous linear system. So we'll go ahead and form the matrix A that corresponds to vectors in the set S. We see that when we row reduce that matrix, we end up with n equals 3 variables in the homogeneous linear system and r equals 3 pivots, so that the only solution of the homogeneous linear system is the trivial solution. Okay, again, when the homogeneous linear system has only the trivial solution, we know that the vectors are linearly independent, the vectors in the set S corresponding to the columns. Here's another example. Determine whether the set of vectors from R3 is linearly independent. Okay, so I'll go ahead and let you work through this one. What you should find is that these vectors are linearly dependent. And as a challenge, go ahead and write a non-trivial relation of linear dependence on these vectors. Okay, since linear independence of vectors is related to a certain homogeneous linear system, and we know that solutions of a homogeneous linear system are related to the fact, related to whether the number of pivots is the number of variables, we have a theorem here, and the theorem is that a set S is linearly independent if and only if the matrix B in row reduced echelon form, where we've reduced the matrix A containing columns from the set S, has R pivots. Okay, so the proof here is pretty cool. It's a sequence of equivalent statements. So let's just go ahead and go through that. So a set S, V1 out to Vn, is linearly independent if and only if the matrix A, where A contains columns from S, has a unique solution. That's true if and only if the matrix B, which is A in row reduced echelon form, has n minus r equal to 0 free variables. And that's true if and only if there are r equals to n pivots. Okay, sort of a take home here is that r equals n pivots, or equivalently non-zero rows, is an indicator of linear independence for this set S containing columns, containing vectors who form the columns of A. Okay, so let's go ahead and think about this set S containing 5 vectors from C6. So to have a look at linear independence of this set, we'll go ahead and form A, where columns of A are elements from the set S. We'll go ahead and reduce that to reduced row echelon form. And here's what we find. Okay, we see that the matrix A has n equal to 5 columns. We see that the row reduced echelon form has r equal to 4 pivots. So we see that the set S is linearly dependent. Okay, in fact, we can pretty quickly see a non-trivial relation of dependence by thinking about the associated solution of the homogeneous linear system. So with that homogeneous linear system, we can see pretty quickly that 1 times u1 plus negative 1 times u2 plus negative 2 times u3 plus negative 1 times u4 plus u5 had better be 0. Okay, so there is an example of a non-trivial relation of dependence. I'll just suggest that you verify that, but that's exactly what it means to be linearly dependent. Okay, here's a set of R equal to 9 vectors from C4. And we don't even actually have to write them all down to see that this set is linearly dependent. We can form the matrix A. We can reduce it to row echelon form. We know that there's no way the number of pivots is any bigger than 4 because there can't be more than 4 non-zero rows. So when we form the 4x9 matrix A and reduce it to row echelon form and pick off R, the number of pivots, R must be less than or equal to 4 because R is also the number of non-zero rows. Okay, so definitely n minus R will be positive. That tells us that the homogeneous linear system has free variables. An infinite number of solutions to that homogeneous linear system tells us that R is linearly dependent. Okay, that's always true and always is a theorem. Suppose that we have more vectors in a matrix than the number of elements in the vector, then S must be linearly dependent. Okay, and the proof in this is pretty quick, right? When A is an M by N matrix here, M rows because each vector is an element of Cm and N columns, then R must be less than or equal to Nm so that N minus R is positive. Okay, this is just a theorem from homogeneous systems of equations where you have more variables than equations restated, but the idea here is that the row reduced echelon form tells us that there N minus R has to be greater than 0 number of free variables. Okay, let's talk about linear independence and non-singular matrices. Of course, non-singular is a characteristic of a square matrix, right? So here is a square matrix corresponding to archetype A, and I'll go ahead and have you use the fact that A is singular to explain why the columns of A are linearly dependent on the worksheet. Okay, similarly, for the matrix B associated with archetype B, I'll have you use the fact that the matrix B is non-singular to explain why the columns of B are linearly independent. Okay, and again, this is something for you to work on a worksheet. Okay, so this turns out to always be a relationship that's true, and when we say always, of course, there's a theorem. And here's the theorem. A square matrix A is non-singular if and only if the columns are linearly independent. Okay, so the proof here is pretty quick, just a short trail of equivalencies. A is non-singular if and only if the corresponding homogeneous linear system has only the trivial solution, which is true if and only if the columns of A are linearly independent. Okay, so here we have a theorem of the form A non-singular if and only if something else. This is an opportunity for us to add to our non-singular matrix equivalencies. And the new addition is that the columns of A form a linearly independent set. Okay, so all of these things are equivalent. Again, I'll remind you that equivalent statements mean that the truth of one implies the truth of all of the others. And the new addition to this non-singular matrices equivalency statement is that A non-singular if and only if the columns of A form a linearly independent set. Okay, so let's talk about null spaces of matrices and their spans and talk about linear independence. It turns out that description we came up with, where the null space of a matrix can be described as a linear combination of n minus r vectors, is actually a linearly independent set. So this is a pretty cool deal. Let's sort of see an example that leads us up to that, and then we'll express it in general. So here is an example. Let's suppose that we have some matrix A, it's 3 by 7, and let's suppose that it reduces to this row reduced echelon form. Okay, now we can pretty quickly write the null space of our matrix A as the span of a set of T, a set of vectors T. Okay, since the null space of A is the same as solutions of the homogeneous linear system, we identify A with 7 columns and B has 3 pivots, tells us that the homogeneous linear system has n minus r equal to 4 free variables. Okay, so here we can express that homogeneous linear system as a linear combination of z1 out to z4. And here we've gone ahead and filled in ones and zeros in our vector form of the set of solutions corresponding to those free variables. Okay, so here are the rest of the vectors, z1, z2, z3, and z4, where the dependent variables in the solution of that corresponding homogeneous linear system come from the columns of the matrix in row reduced echelon form. Okay, now it's pretty quick actually to see that this set of vectors z is linearly independent. Okay, in order to do this, we'll go ahead and have a look at a relation of linear dependence on the set T, right? So a relation of linear dependence is a true statement of the form alpha 1 z1 plus alpha 2 z2 plus alpha z3 plus alpha 4 z4 equal to 0. So by virtue of the way that z1 through z4 is constructed, we can see that alpha 1 z1 plus alpha 2 z2 plus alpha 3 z3 plus alpha 4 z4 equals 0 implies that alpha 1 has to be 0. That's the only choice to get a 0 for the third element. Similarly, it implies that alpha 2 has to be 0. That's the only way to get a 0 element for this fourth element. Similarly, it implies that alpha 3 has to be 0. That's the only way to get a 0 element here. And similarly, it implies that alpha 4 has to be 0. Okay, so the only relation of linear dependence is trivial. So therefore, we see that the set T is linearly independent. Okay, and it turns out the way that we've constructed our spanning set for a null space, we always get a linearly independent set. Okay, so always is a theorem, and here's the theorem. The theorem is suppose that A is an M by N matrix, and we reduce it to row echelon form, and we do our partition, and we cook up the Z sub J's accordingly. Then it turns out that the null space of the matrix A is the span of this set of n minus r vectors, and that this set S has the special property that it's linearly independent. Okay, this is called theorem BNS, and it's really important. We'll come back to it later. Okay, so just sort of to close with an example from last time. Last time we saw that the matrix associated with archetype L has null space given by this linear combination. Now we can express the null space as the span of a linearly independent set. So here's how to do that. I'll go ahead and set the first vector to be z1, the second vector to be z2. The null space of this matrix L is the span of the set z1 and z2. And again, by the way that we've constructed those, the vectors are automatically linearly independent. Okay, this idea of linearly independence and span is going to be really important soon, so keep those in mind. Have a great day, folks. Thanks for your attention. Hope you've learned a lot about linear independence today. We'll see you next time. Bye-bye.